Okay, good afternoon. We had looked at rotor resistance control of induction motor in the last class. And what we said was that if we are going to have 3I2 dash square R2 dash divided by S times omega S as the torque that is developed by the rotor of the induction motor, then we would be able to obtain different values of slip. That is, if we keep R2 dash by S as a constant, which is actually maintaining the torque as a constant, then for every change in R2 dash, correspondingly slip will change, and because of which we would be able to obtain different values of speeds for a given value of torque by adjusting the rotor resistance. This is what we said. And this could be achieved if it can be depicted in the form of the torque slip characteristics. I should say if this is omega R and this is going to be the torque. And if we are planning to maintain the torque as a constant at a particular value, let us say this is our load torque, then we are going to have if the rotor resistance is external rotor resistance is not included at all, if this is the characteristics, if we include more and more resistance in the rotor circuit, we are going to have the characteristics changing somewhat like this. So this is essentially showing R2 increasing or rotor resistance increasing. So correspondingly, we will have different values of speeds attained at a particular value of load torque TL. So if the resistance is minimal, this will be the speed. But when the resistance is increased further and further, we would have lower and lower values of speeds attained. But we already said that rotor input and rotor copper losses and rotor output, if we look at, they will be in the ratio of 1 is to S is to 1 minus S. So this is going to be the ratio of rotor input to rotor copper loss to rotor output. So if we look at rotor efficiency as such, that is rotor output divided by rotor input. So that is going to be 1 minus S divided by 1. So 1 minus S is going to be the rotor side efficiency. So the rotor copper losses will increase further and further if the slip increases or the speed decreases. So this is low speed when we are going to have a larger resistance, and this is going to be corresponding to higher speed. So if we talk about this, this is corresponding to higher speed. So if the speed is higher, the rotor copper losses will be lower. So the efficiency obtained from the induction motor will be better. So that is the reason why rotor resistance control is not a preferred method, because rotor resistance control will increase the copper losses when lower speed is required. Speed operation is required. So naturally, we are going to have lower and lower efficiency at lower speeds of operation. So definitely this is a lossy method. This is going to be a lossy method. So this is definitely not preferred when we talk about induction motors which are of higher rating, and we don't want to waste a lot of energy. That's the reason why we would not like to have rotor resistance control implemented in the case of even a wound rotor induction motor when we want a wider range of speed. At lower speed of operation, we are going to essentially reduce the efficiency quite a bit. So what do we do in that case? So the actual practice which could be implemented to improve the efficiency of the induction motor, wound rotor induction motor, is something called slip power recovery. What we mean by slip power is whatever is S times the air gap power or rotor input. We call that as slip power. So rather than wasting this in the rotor resistance, can we recover this and feed it back to the mains, or can we utilize it in some way or the other? So if we can recover whatever is S times rotor input, so the rotor input generally is specified normally in many of the books as PG, air gap power. So if S times PG, which is the slip power, if that can be recovered, if this can be recovered, then efficiency can be improved rather than wasting it in the form of copper losses. So if this can be recovered, then efficiency will be better. So this is what we are going to look at now, how to recover the slip power. So let me first of all start with if we inject an external voltage from the rotor circuit, from the rotor terminals. How does the motor behave? That's what first we are going to look at. So let us try to see how does an induction motor behave if we are going to inject a voltage from the rotor circuit. That's what we are going to look at now. So let me first of all draw the equivalent circuit of an induction motor. Forget about the resistances and inductances of the stator circuit. So the per phase equivalent circuit, if I try to look at, I'm going to have V1 applied here. And I will have E1 as the induced EMF that is coming across the rotor, the stator winding, per phase winding. Now we are going to have the rotor circuit sitting here, and the voltage that is induced in the rotor per phase is S times E2 if the motor is running with the slip of S. Now we are going to have R2 and we are going to have S times X2 as the reactance. I should also write J times S times X2. That is the reactance of the circuit. And we are normally going to see that this portion is short circuited. Normally this is going to be short circuited. So if we look at the rotor terminal voltage, it will be normally 0. Now rather than that, if I connect a source voltage here, and let me call that as VR, and let us say I have connected it like this. Okay. So now, if I'm looking at what should be the frequency of this VR, that should be equal to the frequency, whatever you are visualizing for this S times E2. Now you can say S times E2 is at a frequency. It is going to be at rotor frequency. So it is going to be at a frequency of S times F1. So if I say that this voltage is at a frequency of F1, then the rotor side voltage is going to be at a frequency of S times F1. So if this is S times F1, even VR should be at S times F1 so that it matches with S times E2. Because if I am supplying two different frequencies to a common circuit, then it can actually play havoc. So that is the reason why we are going to choose a frequency which is exactly same as that of this. And if I say that this is going to be plus and this is going to be minus, and if I want the rotor current, what is flowing here, I want it to be zero. I should have, this should be plus and this should be minus. And we should have SE2 should be equal to VR. And also they should be at the same frequency. The frequency should be same as that of S times E2. So the frequency should be S times F1. In that case, I'm going to have, if these two are equal to each other, if I call this current as the rotor current I2, so I2 will be 0. If I'm going to have SE2 equal to VR and the polarity is going to be somewhat like this, the frequency also should be the same. There is no phase difference. Everything is the same. In that case, I2 is equal to 0. So if I2 equal to 0, then the motor will be on no load. It is going to be not developing any torque because I2 is 0. So in that case, the motor will be on no load. So I should be able to say the speed S or the slip at any point in time. Now slip will be equal to VR divided by E2. So if the stator impedance is neglected, if I'm going to neglect the stator impedance, and if I assume that the stator to rotor turns ratio, if stator by rotor turns ratio is equal to 1, then I should say V1 should be equal to E1. That should also be equal to E2, where E2 is the induced EMF in the rotor circuit at standstill condition. They should be equal to each other. So I should be able to write this as slip is equal to VR divided by V1, where V1 is the per phase applied stator voltage. So this is the applied stator voltage per phase. So in that sense, what we can say is, if we are injecting a voltage from the rotor side, we would be able to adjust the speed even at no load condition as per what is the value of VR that is being injected. So the slip can be adjusted as per the requirement by adjusting the rotor circuit voltage which is being injected from the rotor terminals. So this allows us to control the speed of the induction motor even at no load condition by not really varying the voltage or frequency on the stator side, rather by adjusting the voltage that is injected from the rotor side. We should be able to adjust this particular speed. So let us try to look at 4 different situations. We are going to look at, first of all, sub-synchronous operation. What we mean by sub-synchronous operation is omega r is going to be less than omega s. That is, the speed of the rotor is going to be smaller than the synchronous speed, that is the synchronous speed of the revolving magnetic field created by the applied voltage from the stator side. Okay. So when we look at the sub-synchronous operation, one thing what you have to realize is that if this is going to be my stator revolving magnetic field, which is at omega s, now the rotor is rotating at a lower speed, which is at omega r. So omega s minus omega r divided by omega s is slip. So this is going to be a positive slip value. So the slip value will be positive because omega r is smaller than omega s. Whereas when we talk about super synchronous operation, it will be the other way around. So I can say in general that S times E2 or S times V1, this is going to be positive. So if this is positive, I should be able to say if this is V1 and this is the stator side winding, and if I'm neglecting all the stator drop, this also is going to be V1 with plus here and minus here during the positive half cycle. Now, if this is my rotor circuit, which is going to have S times E2 as the induced EMF, now because slip is positive, I will still have this as plus and this as minus. And when I'm going to have this as plus and this as minus, and let us say the rotor resistance is R2, and rotor reactance, whatever it is manifesting, is S times X2. And I'm going to connect a voltage source here, which I'm calling as VR. So if I want the rotor current to be zero, then I should have very clearly plus here and minus here. Now, let us say the machine is running at a particular speed. Let us say I'm talking about an induction motor, which is a 4-pole 50 Hertz induction motor. Okay. And let us say with certain value of VR injected here, probably let us say I'm going to have the machine running at about 1480 RPM. So this is 1480 RPM and synchronous speed is going to be 1500 RPM. Okay. And let us say per phase voltage, per phase V1 value is 230 volts, 50 Hertz. I'm just taking some values arbitrarily, which is as per our grid values, what we have got. So in this particular case, if I try to calculate what is the slip value, so slip value is going to be 20 RPM divided by 1500 RPM. That is, this is omega R. So omega R, omega S minus omega R is 20. 20 divided by 1500. So 20 divided by 1500 is 0.013. So what I'm going to have is 0.0133 as the slip. So if this is the slip, then S times E2, I should calculate as S times E2. That is going to be 0.0133 multiplied by 230, assuming that there is hardly any drop in the stator circuit. So that is going to be 3.06 volts. So approximately 3 volts. So this is going to be the voltage. So if I try to pump in a voltage of 3.06 exactly in phase with, if I say that its phase angle is 0 degree, this phase angle also should be 0 degree. And if I try to calculate the frequency F2 will be 0.0133 multiplied by 50 Hertz. So this is going to be the frequency. So that is 0.665. This is going to be 0.6665 Hertz. So very, very low frequency voltage is going to be injected. So when I am having a voltage of 3.06 volts injected from the rotor side, this particular machine is going to run at 1480 RPM under no load condition. Now, let us say we are going to, so this is no load condition. So under no load condition, we are going to have the current, what we have got here, I2 should be equal to 0. So this is going to be the no load condition. Now let us say I'm going to put a load. So load is placed on the shaft. So when we place a load on the shaft of the induction motor, we are going to draw a power, mechanical power output. So the mechanical power output is going to be drawn from the induction motor. So the mechanical power output will be positive. So PM will be positive. This is the mechanical power output. So the moment you load the induction motor, the first thing that will happen is speed will decrease. So when the speed decreases, we are going to have from 1480 RPM, probably it will come down to 1460 RPM or 1470 RPM. So we are going to have the speed decreasing. So slip is still positive, but it will increase. So that is going to increase to what value? 1460 means this will be 40 divided by 1500. So this is going to be the slip. So 40 divided by 1500, that corresponds to 0.0266. So we are going to have 0.02666 as the slip value under this condition. So now we will times V1 or S times E2 has increased. So if S times E2 increases, now we are going to see that S times E2 has become double the value of whatever we had got. So about 6 volts or 6.12 volts are going to come up right across this with positive here and negative here. Because slip is still positive, the voltage applied is also positive. Now we are going to have R2 here, S times X2 here, and we have the VR value. VR value remains the same, but the frequency needs to be adjusted. Please remember, the frequency needs to be adjusted. Now this closes the circuit here. Now this is positive and this is negative, and VR value is still 3.06 volts. So what is going to happen is from a higher voltage towards the lower voltage, the current will flow. So we are going to have I2 flowing in this direction. If I2 is flowing in this direction, now VR is getting a current flowing into the positive terminal of this voltage source. So VR times IR is positive, which is actually the slip power. Because this is the power from the rotor side. So this is essentially the slip power. And we also have mechanical power to be positive. And we also know that the slip is positive. So we are going to have VRIR is positive, which is the slip power. Let me write this as PR. PR is the slip power or rotor power. So PR divided by S, that is going to be PG or stator side power or air gap power, or I can call this as rotor input. So this is going to be rotor input. So the rotor input power is also going to be positive because PR is positive, slip is positive. So this will also be positive. So in this particular case, I should be able to say PG, PM, PR and slip all are positive. And we have VR to be positive and IR is also positive. All of them are positive. Okay. Now, on the other hand, if I put a negative load torque put on the shaft. What I mean by negative load torque put on the shaft is just to have a prime mover. If I have a prime mover which is driving the shaft, so that is like inputting a negative torque, negative load torque. So if I am pumping in some torque or mechanical power using a prime mover from the shaft side, now what happens? We have to check. So if I am including a prime mover, then the speed will increase. So I'm talking about sub-synchronous operation still. So originally maybe the speed was 1480 RPM. That's what we said. Now from 1480, let us say the speed goes to 1490 RPM. So the speed has increased slightly. So the slip is going to be still positive, but it is going to be 10 divided by 1500. That is going to be the slip because 1490 RPM is the rotor speed. So 1 divided by 150, that is going to be the slip, which is going to be 0.00667. This is going to be the slip. So this multiplied by 230 volts is going to be the voltage, and the voltage will be S times V1 is going to be 1.53 volts, nothing more than that. Very small value of voltage. Now let us look at the same circuit. So let me try to draw the equivalent circuit of the rotor once again. So I'm going to have the rotor induced EMF now to be 1.57 volts, which is S times E. So this is going to be positive and this is going to be negative. Okay. Now I'm going to have still R2 and I'm going to have S times X2. Now on the other side, I am again connecting the same rotor voltage, but the frequency has to be matched though, definitely. So this VR value is still 3.06 volts with positive here and negative here. So obviously VR value is greater because of which the current will flow in the opposite direction. So we are looking at IR flowing in the opposite direction. So because of which we are going to have VR times IR is negative rather than we are absorbing the power. Now we are supplying the power. So this is negative. So slip power is negative. This is negative. So if slip power is negative and from the load side also PM is actually negative because rather than drawing an electromagnetic torque or electromagnetic power, rather than drawing a mechanical power output, we are trying to put in a mechanical power input through a prime mover. So PM is negative. Now, if you look at the slip is still positive because we already calculated it is 10 divided by 1500. So slip is positive. If slip is positive and PR is negative, PR divided by slip, which is the air gap power or rotor input. The rotor input, because slip is positive and PR is negative, this is going to be negative. Rotor input is negative. So to summarize, I should write it as though slip is positive, VR is positive. These two are positive. But we are going to have IR as negative. So we are also going to have PR, then PG and PM. All these things are going to be negative. So the mechanical power input, rather than taking an output in the form of mechanical power, we are going to have the mechanical power input here from the rotor shaft. So that is also going to be negative. Now the air gap power or generated power, we have a generated power which is positive. Rather than drawing power, it is generating power. And the slip power is whatever we are getting in the form of slip power that is supplied by the external source VR. So that again I'm showing as negative. So here what happens is this is a generator operation at sub-synchronous speed. So what is happening is, if let us say I have a wind turbine, let us say I have a wind turbine and that is being coupled to my induction generator. So the wind turbine may be rotating at a lower speed than synchronous speed. So let us say this is less than synchronous speed. The speed is going to be less than synchronous speed. So some amount of power input comes from the rotor circuit. So these two power put together. So let us say we have some input from the rotor circuit. So electrical input comes from the rotor circuit and mechanical input comes from the wind turbine. These two are added together ultimately to generate a power which is PG, which is the generated electrical power. So this is typically the case when we are using a slip ring induction machine for generating power from a wind energy conversion system. It need not rotate at a speed which is greater than synchronous speed. The speed can be omega r, can be less than omega s. Still, it can work as a generator, provided we supply some amount of electrical power from the rotor circuit. So this is one of the greatest advantages of slip ring induction machine being used along with wind energy conversion system. That's a big advantage. Now what we have seen is only for sub-synchronous operation. What we had seen is now so far for sub-synchronous operation where omega r is less than omega s. That's what we had seen until now. Now what happens if there is a prime mover which will be able to rotate the shaft at a speed greater than synchronous speed? So let us try to look at super synchronous operation. So when we look at the super synchronous operation, let me again draw this equivalent circuit. So let us say this is S times V1. And let's say maybe normally I'm going to have plus here and minus here. And we are going to have R2 S times X2. And here is where I'm going to have VR, which is injected from the rotor circuit. So this is going to be injected from the rotor circuit. So if I'm going to have SV1 equal to VR, if both of them are equal to each other, then that is the no load condition. So the no load slip is given by the equation VR divided by V1. That is what gives me what is the slip or indirectly fixes the speed. If by chance I am going to make this with a reverse polarity. So if I'm going to have plus here and minus here. If I am making it with the reverse polarity, then if VR polarity is reversed, then we are going to have essentially slip becoming negative. So slip will be negative. So if slip is negative, then automatically instead of having plus here and minus here, we should again have plus here and minus here. So if slip is negative, that means omega s minus omega r is negative, which indicates that omega s is smaller than omega r. So when this condition is fulfilled, we are going to have slip to be negative. And we call this as super-synchronous operation because omega r is greater than omega s. So that's what we mean by super-synchronous operation. So as a rule for super-synchronous operation, VR polarity has to be reversed. Only when VR polarity is reversed, we are going to have super-synchronous operation possible. One more thing we have to realize is if this is the induction motor, and I'm going to have omega s like this. And let us say omega r is greater than omega s. So this is omega r. So obviously the difference between these two, which is the difference between omega s and omega r, that is in the opposite sense. So this is going to be omega s minus omega r, what I have drawn here. So that is going to essentially be in the opposite sense. What I mean by this is, if a conductor sitting in the rotor is looking at the revolving magnetic field of the stator, it will look as though it is rotating in the opposite direction. And in the opposite direction, it is rotating with the speed of the difference between omega s and omega r. So that causes the induced EMF in the rotor to be with the negative phase sequence. So if V1 applied is with ABC phase sequence for the three-phase circuit, then SV1 induced in the rotor will be with ACB phase sequence. So it will be with reverse phase sequence because the rotor conductors will visualize the revolving magnetic field as though it is rotating in the opposite direction, but the speed will be omega r minus omega s. The magnitude of the speed will be omega r minus omega s. So not only the polarity is reversed, but the phase sequence is also going to be reversed. So super-synchronous operation, always you will see that the rotor-induced EMF polarity reverses and the phase sequence of the rotor-induced EMF also reverses. Now with this thing in mind, let us try to analyze the super-synchronous operation. So if I am going to have the magnitude of S times V1 equal to VR, if the magnitudes of these two are the same with the VR polarity being reversed, this will be no load condition in the supersynchronous operation. When these two are equal to each other, we are going to have no load condition in the supersynchronous operation. So let's assume this corresponds to something like 1520 RPM. I'm just arbitrarily taking a value. This is 1520 RPM. So the slip is going to be minus 20 divided by 1500. This is what is going to be slip because 1520 subtracted from 1500. So this is going to have a slip value of 0.0133 as the slip value. But this is with a negative sign. So I can say S times V1, again like what we calculated earlier, the voltage is again going to be 3.06 volts, but that is going to be with a negative sign. So this is going to be minus 3.06 volts. So we would see that this is 3.06 volts with plus on this side and minus on the other side. And here also this will have S times V1 is going to be 3.06 volts with plus here and minus here. So under this condition, we are going to have I2 equal to 0. So this is the no load condition corresponding to supersynchronous operation. Now let us say I'm going to put a shaft load. So a mechanical load is applied. So when the mechanical load is applied on the shaft under super-synchronous condition itself, then we will see that speed decreases. So let us say the speed becomes 1510 RPM. So the slip is going to be minus 10 divided by 1500. So this is a negative slip and that is going to be half of this value. And this is going to cause S times V1. That is going to be decreased to something like whatever we calculated earlier, which is 1.53 volts. So this is going to be minus 1.53 volts. So when we talk about this voltage being reduced to 1.53 volts, let me draw this clearly. So this is going to be 1.53 volts with this as positive and this as negative. This is going to be SV1. Now you have R2 here and S times X2 here. Okay. Now we have VR here and VR value is still 3.06 volts. The voltage has not changed. This is going to be 3.06 volts. And let me close this circuit completely. Now this is going to be plus and this is going to be minus still. And the frequency has to be matched with that of what is SV1. And because this particular voltage is smaller than this value, we are going to have a current which is flowing in this direction. This is going to be I2. So I2 will be non-zero and it will be in positive direction. So we are going to have I2, whatever we talked about in motoring operation, this is the direction we talked about, which flows from left to right. If I look at the top portion, the same way here also it is flowing from left to right. This is the way it is flowing. So I2 is positive. But VR is negative. So VR times I2 is going to be negative, which is the slip power. Okay, now slip is negative. So PR is negative, slip is negative. So PR divided by S, which is rotor input PG, both being negative, numerator as well as denominator, that will be positive. The rotor input will be positive. And if I look at the current I2 is positive, so I am going to have the mechanical power drawn from the motor or from the shaft. So PM is also positive. So to summarize what we wrote earlier clearly, like if you look at sub-synchronous generating operation and sub-synchronous motoring operation. So if we look at sub-synchronous, super-synchronous motoring operation, so this is super-synchronous motoring. So in this case, PM and PG are positive. PM is supplied to the load and PG is drawn from the three-phase terminals, and we are going to have PR is negative, slip is negative, whereas I2 is positive. So this is typically the super-synchronous motoring operation, where we are looking at probably a wind turbine which is connected to the shaft of the wound rotor induction motor. It is running at super-synchronous speed. Necessarily, it doesn't mean that it has to generate. It can really work in motoring zone as well. That's what it means. On the other hand, if a negative load torque is applied to the shaft, if we are going to apply a negative load torque to the shaft. Actually, the example of wind turbine, what I gave in this particular situation is not correct. I can rather think about an induction motor is sitting inside an electric vehicle and the vehicle is moving down the gradient. If the vehicle is moving down the gradient, we are going to have automatically the speed increasing. Maybe the speed would have gone to super synchronous speed. Under that condition, I can adjust what is the kind of braking operation that is taking place. That can be done, or how much is the torque developed in the shaft. That can be adjusted by adjusting what is the kind of voltage I'm applying from the rotor terminals. That can actually control the kind of speed that the electric vehicle is operating at. So this is essentially super synchronous motoring region, where the motoring torque that is developed by the shaft can be adjusted as per requirement by adjusting the voltage VR, which is applied to the rotor terminals. Now, let us say I'm connecting a prime mover like a wind turbine to the shaft of the wound rotor induction motor, which is already working at super synchronous speed. Now, under this condition, originally the speed was at 1520 RPM, we said. Now the speed would have increased from 1520, so maybe it has gone to 1530 RPM because we are applying a negative torque. So we are going to have 30 divided by 1500 as the slip. The slip what I'm going to have is 30 divided by 1500. So that is 0.02. So the slip what I have here is 0.02, but this is going to be a negative slip. Omega R is 1530 RPM. So this will be a negative slip. So the slip is negative. Now the voltage that is actually developed on the stator side, that is going to be S times V1, which is minus 0.02 multiplied by 230. So that is going to be about 4.6 volts. So I'm going to have 4.6 volts with a negative sign because slip is negative. So if I try to draw this entire equivalent circuit, I'm going to have here plus and here minus, and I'm going to have 4.6 volts coming up across this particular rotor winding. Now this is R2 and this is going to be S times X2. Please remember this S has to be just the magnitude of S because the reactance, negative reactance really does not make any sense. So this is going to be 0.02 times X2. That is what it is going to be. 0.02 times X2. Now we are going to have this VR connected again, and VR value is 3.06 volts with plus here and minus here. So because of which the current would try to flow in the opposite sense as compared to the motoring operation. So we are going to have I2 to be negative and VR times IR or I2, that is going to be both being negative, PR will be positive. So the voltage source VR will be absorbing power. So which means there will be a power that will be absorbed by this side voltage source as well. Now PR is positive and PR divided by slip. Slip is negative, that is going to be PG or rotor input. PR is positive but slip is negative, because of which PG will be negative. Okay. Whereas if I try to look at PM we already said mechanical power is given by the prime mover. So PM will also be negative. So in this particular case, when I try to summarize, I should say PM is negative, slip is negative, okay, and IR is negative, VR is negative, and PG is negative. So all these things are negative. Only thing which is positive is PR. So PR is going to be positive. So what happens under this condition is we are going to have power generated by both stator side and rotor side circuits. So this is the super synchronous generating operation that would take place in the case of, again, wind energy conversion system. So we can have both subsynchronous generation as well as super synchronous generation in the case of wind energy conversion system. If we are assuming that a wound rotor induction generator is driven by a wind turbine, so under subsynchronous generation, we will have PG, what is generated, that is going to be actually equal to whatever is the mechanical input that is given from the wind turbine plus what is drawn from the rotor side supply. Both of them put together is going to generate the power from the stator side. On the other hand, if we are talking about super synchronous generation, we are going to have stator side supply basically, being generated separately. The generation happens from stator side separately, and from the rotor side, separate generation is going to take place. Both of them put together will balance with what is given as the input power from the wind turbine side, which is running at higher speed than synchronous speed. So in this particular case, we can have the total power generated greater than whatever is the rating of the machine itself. If I am talking about 100 kilowatt induction machine, and let us say the slip is something like 20%. So we are going to have 20% of 100 kilowatt, S times PG, which is going to be 20 kilowatt. That will be generated as PR. And PG is going to be 100 kilowatt itself. So the total power generated is going to be 120 kilowatt, which is greater than the overall rating of the induction machine itself. This is one of the greatest advantages of using a wound rotor induction machine for wind power generating system, where the generation could be greater than the rating of the machine. That is one thing. And second thing is, in both subsynchronous and super synchronous case, the generation could happen depending upon what is the range of slip for which I have designed the entire generating system. So at subsynchronous generation, the generated power may be a little lower, whereas at supersynchronous generation, the generated power will be higher than the rating of the induction machine itself. So this essentially is an introduction to using a wound rotor induction machine for wind energy conversion system. So how can we really inject the voltage from the rotor side? For that, we should know how to implement a slip power recovery scheme or slip energy recovery scheme. So to make things easier, what we normally see is if this is going to be the three-phase supply from the stator side to the induction machine. And let us say this is the induction machine stator. And here is the rotor. So the rotor three-phase terminals are here. Now from here, we are taking out the output. And if we just put a diode rectifier, we don't have to worry about the frequency at which the rotor supply is coming out or rotor terminal voltages are coming out. Diode rectifier will automatically convert any frequency into DC. That should not be a problem. So what we get here is a DC, and let me call that as VD1. Now, we are going to have another thyristor converter connected on the other side. And just to avoid the instantaneous voltage differences, magnifying the current that is circulated through this particular link, we are going to have a reactance or an inductance, which is actually DC side inductance. Now let us say this value of voltage is VD2. Okay. Now from here, we are going to connect the three-phase output, and we can directly connect it to the three phases of this particular three-phase line. So this is how it is connected. So we can essentially, ensure now that this voltage, because it is synchronized with the three-phase power supply, so this will also be at 50 Hertz, although this will be at S times 50 Hertz. So although we are having a variable frequency voltage at the terminals of the rotor, we would be able to get a fixed frequency voltage at the inverter terminals or thyristor converter terminals. And this will ensure that there is a voltage connected across the rotor terminals through the converter-inverter combination at the same frequency as that of the rotor induced EMF. So just to ensure that the system is working in a stable manner, we should always have VD1 equal to VD2. Okay. So if we say that stator to rotor turns ratio is some AT1, I'm going to call that as AT1, then I should be able to write the voltage what comes out here. That voltage I can write as S times V1, which is actually slip times the stator side voltage divided by AT1. That is what is going to come up as the voltage at the rotor terminal per phase. So I can say VD1 is going to be equal to 1.35 times root 3 times S times V1 divided by AT1. This root 3 is because V1 is per phase voltage. So I'm writing it in terms of line voltage, and this is what it is. Now VD2, I should be able to write this as 1.35 V1. That is what is the value that will be available, root 3 times V1, of course, because V1 is per phase voltage. So 1.35 root 3 times V1, that will be the voltage available with plus here and minus here if this thyristor converter had been working at alpha equal to 0. Now here alpha will be greater than 90 because we want this to be plus and this to be minus. Only then the reversal of polarity will occur when alpha is greater than 90. So 1.35 V1 times root 3 cos alpha with a negative sign. That is what will give me VD2. So we should say VD1 equal to VD2 means 1.35 root 3 V1 S divided by AT1 is equal to minus 1.35 V1 root 3 cos alpha. So from which I should be able to write that slip is equal to minus AT1 multiplied by cos alpha. So by adjusting alpha, the firing angle alpha of the thyristor converter, we should be able to adjust the slip or the speed of the induction machine. So here, if you look at it, the feeding back of the power from the rotor circuit is happening through the converter and inverter combination. This is a diode converter, whereas this is a thyristor inverter, which we talked about earlier when we were talking about the regeneration of DC motor drive. So this is a thyristor converter. So two converters are used in this particular case. So we call this as sub-synchronous converter cascade. So slip power recovery scheme or slip energy recovery scheme also is going by the name of sub-synchronous converter cascade. In fact, the implementation was initially invented by somebody by name Scherbius. So we also call this as static Scherbius drive. So the slip energy recovery or slip power recovery goes by all different names. One is subsynchronous converter cascade. The other one is static Scherbius drive. So we will look at slip energy recovery in detail in the next.